Welcome to Physics Can Be Fun with me, Stephen Thomas. Today we're talking about the inverse square law, and in particular how it applies to electrostatic forces and gravitational forces. Now, the inverse square law is something to the effect that the force becomes exponentially stronger as we get very close. So let's, for example, try and illustrate electrostatic forces. Here we've got a little book, some pieces of tissue paper, nothing's happening. Let's rub our hair, rub off some electrons onto this plastic pen, and then let's see if, and there we see how the pieces of tissue paper jump to meet it. But we've got to be quite close before it happens. So it's only as we get very close that the force becomes significant, and that is the inverse square law. Now let's have a look at our law. It says a force. Now here we have Q1 and Q2, which are charges, electrostatic charges, between two normally spherical objects. So we could represent them like this. There's Q1, there's Q2, Q1, Q2, and there's a distance between their centers. So that would be R, the distance between their centers. And the force is pulling it together or pushing it apart. Depends on, we get attractive and repulsive forces. If we have like charges, they repel. If we have unlike charges, they attract. So obviously there were unlike charges between the pen and the pieces of tissue paper for them to jump up. Now likewise, we have force of gravity. Here we have universal gravitational constant. We have a mass 1, for example, at Apple. We have a mass 2, say the Earth. And there's a force of attraction that pulls, and it's always an attractive force that pulls them together. So often in the exam they will ask you to quote a law before you use it. So you have to have the skill set of being able to change an equation like that, which is on your BFF, into words. If we have two electrostatic charges, the centers of which are separated by a distance r, the force of attraction or repulsion, which is an electrostatic force, is directly proportional to the charges and inversely proportional to the square of the distance between the centers of the charges. And that's the whole thing that you've got to write. Now with that experience, let's try it with gravitational forces. We explain the situation. Here we have two objects of mass. Two objects of mass will experience a force of always attraction, gravitational attraction. The force of attraction will be directly proportional to their masses and inversely proportional to the distance between the center of their masses squared. So now we're able to translate that into words. What about this? You'll notice that this one looks similar to that one, but it's only got one charge. So this is the electrical field. So we'll say there exists an electrical field around a single charge. The field strength is directly proportional to the charge and inversely proportional to the distance from the center of the charge squared. So we must be able to put an equation into words. Now we'll perform an experiment fairly soon and show you how this actually applies to real life. If we were to illustrate it, we could say here, inverse square law. Let's say this is the force. Bring them closer together, very much bigger force. Bring them even closer together, super huge force. So that is perhaps how we could get to act it out. And what if they're here and we double the distance? So if that was the original force, it doesn't just half, it becomes a quarter, it becomes much smaller. And if we move them even further apart, the force becomes fractional, tiny. In a darkened room, let's perform an experiment which illustrates the inverse square law. So what we've got is we have a lamp here. We have the blackboard exactly 1 meter away, and we have another book set up 1/2 meter away, and I'm going to get an identical book, and let's draw on the blackboard the outline of the book. There's the book. So there's the size of our book. Now we take an identical book and put it half the distance from the light source. Let's switch on the light source and let's trace the outline of the shadow. Now the outline of the shadow we can see is about there. So that is the outline of our shadow. Let's just switch this off. And you will see there's the original book. Here is the book when it's half the distance. Now let's get a tape measure and let's bring this till it's a third of the distance. So here it was 1 meter, half a meter. Let's bring this so that it is 33 centimeters. And there we go. Now let's see what size shadow it casts. So as you can see, that is the size shadow that the same book casts when it is 1/3 of the distance away. Now we've performed our experiment. We've got our 3 shadows. As we bring the book closer, which shadow represents when the book is the closest to the light bulb? The bigger. So we have a relationship here where the closer or the smaller the gap, the bigger the shadow. We call that an inverse relationship. But why is it an inverse square relationship? Because we are decreasing this distance between light source and book, we are finding and experiencing increase not only in width but in height. So we're getting a square increase. And this relationship is obvious with light. Let's suppose we had a distance, which we did have, of 1 meter. Let's call that R, the distance was 1. What was our folio? Or let's call this a folio. We had, when this was 1 meter apart, we had 1 folio's worth of shadow, and there it was. So when this was 1 meter away, we had 1 book's worth of shadow. When we had half of the original amount, what did we have? We had 1, 2, 3, 4 books worth of shadow. So we found that our folios became 4 lots of shadow. The shadow had increased 4-fold in area. So let's just say this is the area there. So that was when we had half the distance from source to book. And then when we moved the book to 1/3 of its original distance, when R, that's 1/3 of a meter, we found that this had increased by 1, 2, 3 books, and 1, 2, 3. So we've in fact got 9 books that would fit in here. So this becomes 9. What are we seeing? We're seeing 1 upon the square inverted becomes 9. So 1/3 squared and then inverted is a 9. So that is your inverse square law as it applies to a light source. Now, if we do the same thing I'm going to show it here. Let's suppose we look at this formula. This formula, the relationship between F and R is the same. It's an inverse square relationship, and it doesn't depend on those. Those can be any values, and that relationship stays the same. And in fact, R can be any value, and the relationship between F and R stays the same. So why don't we do something and just make all of that equal to 1, because we can. It makes no difference to the relationship. Let's make that 1. So if F equals 1 upon 1 squared, what's F going to be equal to? Well, 1 upon 1 squared is 1. So F is going to be 1. So if instead of having folios we have force, if our distance is 1, our force is 1. Now let's do the same. Doesn't matter which formula we choose. The relationship between force and distance is independent of those, so let's make those 1. So we have 1, and let's make that a half. Let's make this half the original distance. So we have 1 upon a half squared. We square the 1, we square the 2. So we get 1 upon 4, inverting it, because 1 upon 4 is the same as 4. So we see the same relationship here. When R is a half, F is 4. And likewise, when this becomes a third of the distance, 1 upon a third squared is equal to 9. A third squared, so when that is a third, E, the electrical field strength, is 9. Obeys exactly the same relationship as we see with the shadow. So what is an inverse squared relationship? It's a relationship where as you change one dimension, you change 2 dimensions, which we call a square. Now, if this is a light source, it's giving out light in all directions like that. And as we bring the book closer, it cuts more and more rays and leaves a shadow in its wake. Now, the same thing applies with a charge. This could equally be a positive charge, which has electrostatic field lines. And as we bring another charge closer, the charge cuts more and more of these field lines. I've only drawn a few of them. But because there are more field lines, it means a stronger field. And likewise with gravity here, as you come close to a black hole, nothing happens. But then as you change even a little bit of the difference of the distance, because of the inverse square law, you're going to get sucked quickly into that black hole. It's like when you use a magnet. So you've got a magnet, you bring it, nothing happens, and then suddenly the pins jump to the magnet. Or you take electrostatic charge, like we started off, you charge your ruler, pieces of tissue paper, nothing, suddenly there's a huge increase.